So, since the emergence of mass-produced plastics in the 1950s, the global appetite for these materials has been increasing at a really rapid rate. And you can see back in 2013, we were actually producing about 320 million metric tons of this material every year. And what I find alarming that is if we continue down this road, that by the year 2050, it's estimated that we'll be making about 1.8 billion metric tons of plastic every year. And now you can see that this study is quite dated. And what we're finding now that thanks to the pandemic, we're actually north of these estimates now. So back in 2013, it was estimated that the total production of plastic was about 8.3 billion metric tons. And anytime we're making this much of this material, we really have to ask ourselves, well, where is it going? So at the time, it was estimated there's about 6.3 billion metric tons of cumulative plastic waste out there. And this pie chart on the bottom right here shows you that actually the vast majority of this material is finding its way into our landfills in the natural environment, where only a small percentage is recycled or incinerated. So as a result of this, now plastic is basically ubiquitous in the environment. Everywhere we look, we find it. And we really don't know what the ecological impacts or the human health impacts are, but the things that we can say are these materials are extremely persistent. They've been designed to last forever and they don't go away. They just break down to smaller and smaller sizes. So we got roped into this microplastics thing about 6 years ago when John Kelly had called me and asked me if I can help identify some of the plastics he was finding in the samples. And our lab possesses a unique capability called pyrolysis GCMS that's great at doing polymer identifications. So I really have him to thank for this, getting me into this field. But really, since that time, we've really expanded into all different facets of the plastic realm. And we've done things like looked at additives and contaminants in plastics. In fact, we've even found rare earth elements in some consumer plastics. We've done a lot of work with looking at how these plastics will absorb environmental pollutants. We are doing work looking at how these things weather and how they degrade. And the things I want to kind of touch on today is also that we've done a lot of work in the area of microplastics analysis. We've developed some methods in-house, and obviously we've applied those methods now to environmental samples, and now we're trying to use these tools to further this research. So right now, the closest thing that we have to a standard method are methods developed by NOAA back in 2015. And we've actually used this as a template, but we've actually made some modifications to this method, or some improvements, in my opinion. And the first one that we've really focused on is this initial sieve. And if you're following the NOAA method, the smallest size that they can capture was about 300 micron. We've actually fabricated some stainless steel sieves, and we believe that we can get down to about 20 by 20 micron for a particle size. And when this is important, because what you find is that you get to smaller and smaller sizes that we see more and more occurrence of plastic. And the other thing that we focused on was this density separation step. This removes the polymers from the inorganic material, but we have fabricated some apparatus, and we've actually played around with salt solutions a lot, and we were able to get a much higher density than the current NOAA method. The NOAA method uses sodium chloride. It only gets you to a density of about 1.2 grams per cubic centimeters. We can readily get to 1.8 grams per cubic centimeters. And the importance of this is we can actually capture a lot more polymers. And this gets really important when you think about things like sediments, because you expect them to contain the heavier polymers such as PVC and polyester and all the other types of materials that are out there, because a lot of people may be actually missing these materials. And down here is our technical report in case anybody wants the nitty-gritty details. You can see this was published last year, though, and we've actually made even more improvements on this method with in mind that, so you can do further polymer identification downstream. So we're still working improving our method, but right now this is the working one that we have. So now that we have this method, one of the things that the other thing I want to talk to you about, the most important thing I want to talk to you about is how we report microplastics. And when you look in the literature, you see everyone's using this unit of numbers per liter, particles per fish, or particles per kilogram. And I really think that we need a revolution in the reporting of microplastics. Many of these materials are very, very weathered, and they're most likely breaking down when we do our magic in the lab. You can have a particle that it was originally 500 micrometers, but after we're done doing all our magic, we might actually break that down into 10, 50 micrometer particles. So I believe that makes the style of reporting makes it very difficult to compare data from sites and from within studies, and it really doesn't provide any information that's useful to the people doing modeling and toxicology. So we adopted this approach to actually Lee does very painstaking measurements of the microplastics she finds, and we try to estimate the mass of the material there. And we think that this is very important. So this is our approach, and this is an example down here on the right of one of the microplastics, but this is a number that we can really use, and we can definitely compare, and it's so important. We really need a revolution in how we report these things. Let's see. So the other thing is we had this method, so we decided to apply it to some biological tissues, and we really like fish larvae. And the reason why we like them is because we can get 1,000 of them in a single composite. And these guys are really sensitive to environmental contaminants, more so than later in life fish. And they are particle feeders. You know, they kind of go after and try to gobble up all the particles that they can find around them. And they have very high metabolism and high prey rate consumption. So they're an ideal test subject. And the other nice thing is our colleagues, Joe Parkos and Dave Suchek over at the Illinois Natural History Survey actually have a giant collection of archived fish larvae. They have drums of these things. And we were able to get a pretty large size of samples that are, well, not only spatially distributed, but also temporally, going back to 2013. So this was a great media for us to test out our methods and see how they perform with biological tissues. So let's see. Here's some preliminary results. And here on the left, you can see this is the color of the plastics that we found, and the vast majority of it was blue, gray, and black. But we really don't know if those were the most abundant colors that were in the water column, or if these guys are preferentially going after and trying to gobble up these colors. Maybe they resemble to prey. And the same thing is for the shapes, which are here on the right. You can see the vast majority of microplastics were fibers with some fragments and pellet from time to time. But again, we don't know if this was the most abundant in the water column, or do these guys seek this stuff out specifically. So that alone would be an interesting follow-up study to do. The other preliminary set of data I'd like to show you is here on the upper left is the number of larvae analyzed. And you can see we did about 16,000 total fish larvae. And on the upper right here, you can see the number of plastics that we found. So, but we have to normalize that, right? Because if we looked at more larvae, then you would logically think we would find more plastic. And the take-home message here, though, is if you look here on the bottom right, we used our mass estimates and we normalized them to the number of fish analyzed. You can see this Havana site just pops right out. So if we were to normalize it under just number of plastic, the Havana, Lily, and Peoria would look very similar. But when we take into account the mass of plastic we found and not the counts, it definitely pops out, and it's very interesting. So this is a fishing expedition, if you will. We plan on hoping to do some more follow-up studies. We just kind of wanted to see how our methods perform and generate some preliminary data, and we are still working this up. But anyhow, I think we really need a revolution in the way we report these things. And not only that, the sizes. When you look at the data that's reported for the sizes of microplastics, you have to ask yourself, is it being influenced by how we're processing the sample? And does that really reflect what we find in the environment? And I'm way early, but I would like to open it up for questions or discussion if anybody would like to.
Absolutely. We can take several questions, Lee.
Okay. Is that an assumption that particles break down during sampling analysis, or have you seen that firsthand?
Well, I haven't seen it firsthand, but it is more than likely going on. In fact, some of the images I showed you earlier of SEM and infrared mapping that we've done, we know that these things are very weathered. So I don't know. I don't know there's a way to really easily check to see if it's happening, but I highly suspect it's going on. And we also see it with our water data as well. There would be sites where we would find 5 plastics per liter and sites where we find 200 parts per particles per liter. But when you look at the mass of the plastic, they were really quite similar.
Do we have time for another question?
Yep.
Another thought for the observation of the high amount of fiber in the fish larvae. Could it be that it is harder to digest and is more likely to get stuck and accumulate in the gut?
Yeah, absolutely. That's something that could possibly be going on. And that's another good question. You know, how long do these guys retain these materials in their gut? You know, I've tried to do some risk assessments before, and that was one of the problems I ran into is, you know, a lot of this data out there is just a quick time shot. We really don't know how long this stuff sticks around inside of an organism. And I'm sure it has a lot to do with shape. You're right. Hopefully I answered your question.
We have time for a couple more.
Okay. Have you gone back to compare and analyze your recent findings to the fish that were collected in the past?
Yeah, you know, Tim and Ray and just Tim Holine and Ray McNesh just published a paper where they got some archive museum samples as well, and they just published on that. So we have not done that, but it would be cool to do. And yeah, it's pretty interesting. One thing you got to be careful of, though, these archive samples, you really don't know how they were collected. So there is always the potential for contamination because they, you know, plastic was an afterthought. So, you know, moving forward, we can prevent the contamination, but from archive samples, we can't.
John, were the larvae free of plastic before your tests?
Yeah, I believe so. I think we rinsed them off. If not, I guess I'd ask you that question, Lee. I believe that they were rinsed off beforehand, especially when they were counting them. I believe Joe's group had rinsed them off when they were counting them. So we should only be accounting for what's in the gut or in the gill or in their tissues.
Correct. Got a couple of comments that just said, very interesting, thank you.
Were the fish larvae collected from the environment, or were they
No,
lab samples subjected to microplastics?
they were from the environment, Beth. Yeah.
Okay.